Hi everyone, welcome to our channel NCERT Science. This video is a continuation of the NCERT Science Class 9 series, and today we will be talking about Chapter 3 in NCERT Science, Structure of an Atom. So this is the last chapter in chemistry for Class 9, and we will be starting biology in the next chapter. So before I start the video, I just wanted to mention that this video will also be helpful to those preparing for NTSE, NEET and JEE, in addition to those preparing for CBSE exams. So I encourage you to take your own notes. Like I say in every video, take your own notes. I will be presenting in my own words. I took pictures from the NCERT textbook that I found online. And I will be presenting in my own words, but I don't want you to write down everything that I say. I want you to note down important points in your own words, because that will help you remember better. Alright, so whenever you have any question, feel free to pause or rewind and watch again and reach out for help. You can ask your friends, your teachers, but make sure you listen to the concept very carefully. Alright, so so with that said, let's jump right in and start with Chapter 4, the structure of an atom. Alright, so this, as I said before, this is the last chapter of chemistry, so please pay attention. This is also a very important chapter that will play an important role in the coming chapters of chemistry. So it would be very helpful for you if you pay attention. Alright, so let's start with Chapter 4, Structure of an Atom. Structure of an atom. Alright, so in Chapter 3 we've learned that atoms and molecules are the fundamental building blocks of matter. The existence of different kinds of matter is due to different atoms constituting them. The questions arise: what makes the atoms of one element different from the atom of another element, and are atoms really indivisible as proposed by Dalton, or are there smaller constituents inside the atom? So we discussed Dalton's atomic theory in the previous lesson. If you haven't watched that video, please go back and watch it for you to get the flow of the course. And so they're asking if atoms are really indivisible, or whether they can be divided into smaller particles. And then we have introduction again, and we start with the charged particles in matter. So there are a couple of activities here that I will read out to you today. The first activity says comb dry hair. So don't comb oiled hair. Comb dry hair and place the comb near small bits of paper. Does the comb then attract these pieces of paper? This is what we used to do this with the plastic ruler as well in school. So let me tell you the outcome of this experiment, but I encourage you to still carry out this experiment at home. So let's just say this is a plastic ruler. Right? I don't want to draw a comb. This is a plastic ruler. It has all these divisions. Okay, and there are small bits of paper here. Alright, so once you comb dry hair, or once you rub dry hair with this and you put the ruler near the small pieces of paper, you will observe that the pieces of paper attract towards the ruler. It's very fun to watch, to conduct the experiment, and by the end of the lesson you will understand why this happens. Alright, so from these activities, can we conclude that on rubbing two objects together they become electrically charged? Yes. And where does this charge come from? Alright, this question can be answered by knowing that an atom is divisible and consists of charged particles. Alright, so that's an important statement. An atom is divisible. Contrary to Dalton's atomic theory and contrary to the postulates of early Indian and Greek philosophers, an atom is divisible. It is not indivisible. It can be divided into subatomic particles. That's what we call them. Subatomic particles are particles that exist below the level of the size of an atom. Alright, so subatomic particles. I'm going to go ahead of myself and list them out to you. Protons, electrons, and neutrons. So protons, electrons, and neutrons. These are the subatomic particles. Alright. So many scientists contributed in revealing the presence of charged particles in an atom. There wasn't just one scientist who discovered all three substances in one day. There were many decades of experiments, and many scientists who put in a lot of work to discover protons, electrons, and neutrons. Alright, so the electron was identified by J.J. Thomson, and even before the electron, E. Goldstein discovered the proton. So he called this canal rays. So these were the radiations, positively charged radiations in a discharge tube. So canal rays were the positively charged radiations that led to the discovery of protons. Alright, so these canal rays ultimately led to the discovery of another subatomic particle, and this particle had a charge equal in magnitude but opposite in sign to that of the electron. Alright, so if the charge of an electron was -1, the charge of a proton is +1, right? So it's equal in magnitude. Magnitude is the number here. They're equal in magnitude but opposite in charge, right? Opposite in sign. So this is negative, this is positive. Equal in magnitude but opposite in charge. Alright, that's how a proton and electron are related. Its mass was approximately 2000 times as that of an electron. So for the sake of simplicity, I'm going to say the mass of an electron was 1. This is not true, but for the sake of simplicity I'm saying this. And so the mass of a proton would be 2000. Alright, but in reality the mass of a proton is 1 AMU or 1 unit. So the mass of an electron is negligible. Alright, proton has 1 unit mass, and the mass of an electron is negligible. Alright, this doesn't look very nice, so I'm going to write it again. E. Alright, this is why we even represent E as E minus with the minus symbol in a circle. This is how we represent electron, and this is how we represent a proton. Alright, and then we have, right, so an electron is represented as E minus and a proton is represented as P plus. The mass of a proton is taken as 1 unit and is charged as +1. This is also why it's written as P11. That means the proton has a charge of 1 and a mass of 1. And the mass of an electron is considered negligible and its charge is -1. Alright, so initially after the discovery of protons and electrons, scientists thought that was the last level. They were the only 2 subatomic particles, but then a case of logic, I should say, led to the discovery of neutrons. Alright, and we'll talk about that later in the lesson. So so there was this big question that said, what sort of structure did these particles of atom form? And that's what the next part of the lesson will be, the structure of the atom. All right. So we have two questions here. Water canal race, that's what I just explained above. And if an atom contains one electron and one proton, will it carry any charge or not? So if it has an electron which has a negative charge and a proton which has a positive charge, the positive and negative get cancelled, and that leads to no charge, right? So that would be the answer for this. So the structure of an atom, we learned about Dalton's atomic theory in chapter 3, which suggested that the atom was indivisible and indestructible, right? But the discovery of two fundamental particles called electrons and protons inside the atom led to the failure of this aspect of Dalton's atomic theory. So it was necessary to know how electrons and protons were arranged within an atom, all right? Because nobody knew now, because all this while they thought an atom was just an atom, it wasn't divisible. But then suddenly they discovered electrons and protons, so everybody was trying to understand how the structure, how an atom is structurally arranged. All right. So there were many atomic models, and first we're going to look at Thomson's atomic model. So Thomson, if you remember, J.J. Thomson was the person who discovered electrons. All right, discovered electrons. That was him, and he put forward a model for an atom. All right, so he proposed the model of an atom to be similar to that of a Christmas pudding. We also call this the plum pudding model. Plum pudding, and I believe we also call it the watermelon model. I will explain why. So the electrons in a sphere of positive charge were like the dry fruits in a spherical Christmas pudding. So the electrons were embedded all throughout this positive sphere. All right, so if you imagine a pudding, this would be the actual pudding, the positive particles, and the electrons would be the dry fruits in the pudding, right? That's why it's called the plum pudding model. And if you take the watermelon model, why it's called the watermelon model, if you imagine a watermelon, the positive part, the positive sphere is the red part of the watermelon, right? And then the electrons were the black seeds, right? So now that I shaded it likewise, it does seem similar to a watermelon, right? So that's why it came to be known as the watermelon model. And Christmas pudding and the plum pudding are the same thing, so that's why they're all also interchangeable. We can also think of a watermelon where the positive charge in the atom is spread all over the red edible part of the watermelon, while the electrons are studded in the positively charged sphere like the seeds in the watermelon, right? And then we have a little trivia information about J.J. Thomson. You can read about him later. And so Thomson proposed that an atom consists of a positively charged sphere and electrons are embedded in it. All right, this is the first postulate. And the second point that he gave was that the negative and positive charges are equal in magnitude, right? So the atom as a whole is electrically neutral. So now let me tell you, this was rejected later on, but this is true even until today. All right, this was proved false later on, the first point, but the second point is true until today. Although Thomson's model explained that atoms are electrically neutral, the results of the experiments carried out by other scientists could not be explained by this model, as we will see below. So this one is what they were talking about. Okay, so the first point was contradicted by the experiments of later scientists, but the second one is held true even until today. And then we have Rutherford's model of an atom. Ernst Ernest Rutherford was interested in knowing how the electrons are arranged within an atom, so he designed an experiment called the alpha particle experiment. And in this experiment, fast-moving alpha particles were made to fall on a thin gold foil. All right. So, if a question is asked, let's say how was Rutherford's experiment set up? So you can say Rutherford's experiment was set up in a way that fast-moving alpha particles were made to fall on a thin gold foil. All right. So he selected a thin gold foil. So this is so these are the reasons why he did what he did here. So he selected a gold foil because he wanted as thin a layer as possible, and gold is highly malleable. Okay, so we learned about malleability and ductility. Gold is highly malleable. All right, and alpha particles are doubly charged helium ions. Since they have a mass of 4U, the fast-moving alpha particles have a considerable amount of energy. So it's hydrogen, helium, lithium, right? The masses of these are 1U, 4U, and 7U. All right. So the mass of an alpha particle, which is essentially helium, let me write this here. An alpha particle, that's how alpha is written. An alpha particle is the electrons removed from a helium atom. All right. So helium has atomic number 2, so it has 2 electrons, and if we remove those 2 electrons, that's what forms an alpha particle. All right. So that would also be equal to helium plus 2. Okay, this is very important. All right. So helium has a mass which is neither as light as hydrogen nor as heavy as lithium. So it has a moderate mass, which is why they have a considerable amount of energy. Alpha particles have a considerable amount of energy because helium has a moderate mass. All right. And it was expected that alpha particles would be deflected by the subatomic particles in the gold atoms. So if you go by Thomsons Model, if an alpha particle strikes an atom, because of the uniformly arranged electrons, almost all electrons are supposed to be deflected, right? When you have, let me switch colors here. So when you have many alpha particles, like so, what Rutherford expected was that most of them would be deflected because of the uniform presence of electrons in an atom as suggested by Thomson. But let's see what he actually found and how it changed our view of the structure of an atom. But the alpha particle scattering experiment gave totally unexpected results, and the following observations were made. So most of the fast-moving alpha particles passed straight through the gold foil. All right. So most of them, if you see these, most of them passed straight through without any obstruction, without being deflected. Some of the alpha particles were deflected by the foil by small angles. By small angles, there were some, but very few particles appeared to rebound. That means they were deflected by large angles. So 1 out of every 12,000 particles appeared to rebound. So this showed that there was no plum pudding structured atom, right? Because if you went according to Thomson's model, almost all particles were supposed to be deflected or rebound, but that's not what happened. Almost all the particles went through undeviated. They went through without undergoing any deflection, right? So they just passed through like this. But if that were to happen in Thomson's model, the electrons would have to take a curved path, which is not the alpha particles would have to take a curved path, which was not possible, right? So that showed that Thomson's model was in a way wrong. Alright, so and then we have a little information about Rutherford here. So based on the experiment, the following conclusions were made. Most of the space inside the atom is empty. Most of the space inside the atom is empty. Most and empty, those are the keywords here. And why did he reach this conclusion? Because most of the alpha particles pass through the gold foil without getting deflected. Alright? And then the second point said very few particles were deflected from their path, indicating that the positive charge of the atom occupies very little space. So positive charge and very little space, they are the keywords here. And why did he reach that conclusion? Because very few particles were deflected from their path. Alright, and a very small fraction of alpha particles were deflected by 180 degrees, indicating that all the positive charge and mass of the gold atom were concentrated in a very small volume within the atom. So in this point, so this is the second point, and so in the third point, all the positive charge and mass of the gold atom were concentrated in a very small volume within the atom. Those are the key points here. And why did he reach this conclusion? Because a very small fraction was deflected by 180 degrees, right? So on the basis of Rutherford's experiment, he put forward a model which said there is a positively charged center that had never been thought of before. A positively charged center in an atom called the nucleus. Nearly all the mass of an atom resides in the nucleus. So we have to keep in mind that this was before the discovery of neutrons. Keep this in mind and I will tell you why. Alright. The second point said the electrons revolve around the nucleus in circular paths. That was the second point. And the third point was that the size of the nucleus is very small as compared to the size of the atom. Alright, so I would like to tell you right now that all 3 points hold true even to this day, with a few modifications of course, but the basic structure, the skeleton that he gave was true and it is still true. Alright, so there were a few drawbacks and of Rutherford's model. Because the revolution of an electron in a circular orbit is not expected to be stable. Because when you're continuously moving, so this is what Rutherford put forward. He said if this is a nucleus, if the green part is the nucleus, the red and blue parts were to be the, let's do that. They were the orbits, or they were the circular paths. So let's take black. So if this is an electron right here, and if this is an electron right here, they're continuously moving, right? They're continuously moving, I don't know, clockwise, anti-clockwise. So when they're continuously moving, they lose energy, right? When you're continuously playing all day, you lose energy. You're not going to be as energetic as you were before you went out to play. So what other scientists of that time contradicted his model by saying is that if they're losing so much energy, how come they're not falling into the nucleus? How come they're still able to move around the nucleus in the same orbit, in the same circular path, when there is a change in energy, right? That's what they said, because if the electron fell into the nucleus, that would make the atom unstable, right? So they questioned the stability of the atom and they said, no, your model cannot be right. Alright, so during acceleration, charged particles would radiate energy, thus the revolving electron would lose energy and finally fall into the nucleus. If this were so, the atom should be highly unstable and hence matter would not exist in the form that we know. So that's how they rejected his model. And then Bohr came along to give his model of the atom, and he said in order to overcome the objections raised by in order to modify Rutherford's model of the atom, he put forward a few postulates about the model of an atom. Only certain special orbits known as discrete orbits of electrons are allowed inside an atom. This is true even today. And while revolving in discrete orbits, the electrons do not radiate energy. That was the second point. Alright. So this is information about Bohr again. All this is information about Bohr. So according to Bohr, this is the structure of an atom. And if you if you remember, this is what we still use, right? This is how our structures of our atoms look like when we're learning how the structure is. So he called each orbit energy levels. Okay. And he said that each atom has a specific and certain energy level. When an electron is here, let's say, let's not use black because that's how they depicted the nucleus. So if an electron was here, if it absorbed energy, it would move on to this next energy level, alright, so the next orbit. So it would be here. And if it lost energy after some time, it would lose energy and fall back to the previous energy level, which is closer to the nucleus. Alright, and so he named these the K, L, M, N, and so on shells, or you can also say shell number 1, shell number 2, shell number 3, shell number 4, and so on. Okay. Alright, so we have a few more questions here. On the basis of Thomson's model of an atom, explain how the atom is neutral as a whole. So Thomson said that there is a positive sphere in which negative particles are embedded uniformly. So the positive and the negative together, they get cancelled. Alright, that's how he explained the neutrality of an atom. On the basis of Rutherford's model of an atom, which subatomic particle is present in the nucleus of an atom? It's proton, because he said the nucleus consists mainly of the positive charge, contains the positive charge of the atom. That's what is in the nucleus. That is the proton. Draw a sketch of Bohr's model of an atom with 3 shells. Alright, so first we draw the nucleus, and then we draw the first shell, then the second shell, and then the third shell. Alright, they're supposed to be circular. They came out elliptical, but they're supposed to be circular. Let me say circular here. Alright, circular shells. And I stopped with 3 because they mentioned here draw it with 3 shells. So whenever you're reading a question, read it carefully, see what they actually asked you, instead of reading until Bohr's model and drawing only 2 or drawing 4. Read what they want you to do and continue with the question. Alright, so that's the third question. And what do you think would be the observation if the alpha particle scattering experiment is carried out using a foil of a metal other than gold? So more or less the results would have been the same, because most metals are malleable, but gold is highly malleable. So if the experiment was carried out using some other metal, it would not have been as accurate as it was when he used gold. Alright, so that's the fourth question. And then we have neutrons. So James Chadwick discovered another subatomic particle in 1932 which had no charge and a mass nearly equal to that of a proton. It was eventually named as a neutron, and neutrons are present in the nucleus of all atoms except hydrogen, because hydrogen has 1 proton and 1 electron, so it has no neutrons. Alright, so a neutron is represented as a small n, and the mass of an atom is given by the sum of the masses of protons and neutrons present in the nucleus together, protons and neutrons are called nucleons because they're present in the nucleus together. So let me tell you how neutrons were discovered. So Chadwick was thinking, if there is if the mass of an atom was, let's say, 20 grams, this is a hypothetical example. If it was 20 grams, he observed that the mass of a proton was only the mass of the proton of that atom, let's say X, was only 10 grams. And we already established previously that, so this is for a proton. We already established that electrons have 0 grams, negligible mass, so we're taking 0. This is electrons, this is protons. Alright, so he thought, if the mass of a proton and the mass of an electron don't add up to the actual mass of the atom, and they're roughly equal to half the actual mass, this is equal to half the actual mass, what about the rest of the mass? Where is the rest of the mass of the atom? So he thought there's probably a third subatomic particle with a mass roughly equal to the mass of a proton. So if that is 10 grams, it would add up to 20 grams. But then he thought, so if the proton is positive and if an electron is negative, what should the charge of the third particle be? Because if the charge of the third particle was positive, the overall charge of the atom would be positive, and if the charge of the third subatomic particle was negative, the overall charge would be negative. That's not true. The overall charge on an atom is neutral. So if this is positive and if this is negative, the charge of the third subatomic particle should be neutral, right? Should be 0. It shouldn't have any charge. That's how he came to the conclusion that a neutron is a particle that has no charge, that means it's neutral, and a mass nearly equal to that of a proton. Alright, that's how he came to the conclusion. Name the 3 subatomic particles of an atom: protons, electrons, and neutrons. Alright, and the 0 on top of neutrons represents 0 charge or neutral or its neutrality. Alright, helium atom has an atomic mass of 4U and 2 protons in its nucleus. How many neutrons does it have? 2. Alright, simple. Okay, so then how are electrons distributed in its different orbits? The distribution of electrons into different orbits was suggested by Bohr and Bury. So the following rules are followed for writing the number of electrons. These are very important rules, and I want you to pay attention because this will help you write the electronic configurations for different atoms in the coming lessons. Alright. So the first rule says that the maximum number of electrons present in a shell is given by the formula 2n square. 2n square. This is very important. The maximum number of electrons present in a shell is given by the formula 2n square, where n is the orbit number of the energy level index. Okay, so the maximum number of electrons in the K shell is 2 times 1 squared, because K shell is the first one, L shell is the second one, M shell is the third one, N shell is the fourth one, and so on. Alright, so for K shell it is 2 times 1 square, which is 2. For L shell it is 2 times 2 square, which is 8. For the M shell it is 2 times 3 square, which is 18, and for the N shell it is 2 times 4 square, that is 32. And there are and then you have other following at orbits. So this is the first level, that's the first rule you're supposed to remember, the first step. And then the second step says the maximum number of electrons that can be accommodated in the outermost shell is 8. This is a very important rule. I will tell you why, but this is a very important rule. Keep this rule in mind, and be cautious when you're writing the configurations of different elements. All right. And the third one says electrons are not accommodated in a given shell unless the inner shells are completely filled. All right. So the shells are filled in a stepwise manner. If you have 3 shells and if you have 4 electrons, right? So you can't fill one here, one in the outermost shell, one in the innermost shell, and one in the middle shell, and then you distribute the remaining 1 electron wherever you want. That's not how it works. All right. The electrons are not accommodated in a given shell unless its previous shell is completely filled. Okay. So the third electrons cannot be put in the third shell unless the second shell is completely filled, but the electrons cannot be put in the second shell unless the first shell is completely filled. That's what you need to remember. All right. That is also pretty important. Okay. So the atomic structure of the first 18 elements is shown here. This is very important. Go through this diagram, go through this representation, and make sure you understand what's happening, because the first one, for hydrogen and helium, there's only the K shell, right? And the maximum capacity is 2 because of 2n square, and the maximum capacity for K is 2 electrons, right? And then if we move on to the second row, it has the K shell here and the L shell. Okay, so the whole if this is the first element, this is the second element. 3 through 8 have only the K and L shells, right? And the L shell can have a maximum of 8 electrons in it, right? 2n square again. That's why it can have a maximum of 8. All right. So until you reach 8, you cannot move on to the next one. And in elements from 3 through 10, I mean. This was 10. This was supposed to be 10, not 8. I'm sorry about that. So from elements 11 through 18, they have K, L, and M shells, and even the M shell can hold a maximum of 8 shells only. Okay, because if you see here, the next one, for the next element, which would be potassium, its symbol is K because its Latin name is Kalium. Remember from the previous lecture, potassium is K. So if it has one nucleus, K shell, L shell, M shell, nope, too thick. Alright, K shell, L shell, M shell, and N shell. If it has the N shell, then the outermost electron, the outermost orbit should have only 8 electrons, which is why this would stop with 8. Okay, even though it's the M shell, it won't continue to have 18 electrons in it. All right, and then we have it just wants to move up. Yeah, okay. And then we have 2 questions. Write the distribution of electrons in carbon and sodium atoms. So for carbon, it would be 2 in the first K shell, comma, that's how we represent this, comma. In the L shell, there would be 4 electrons. For sodium, this is because the atomic number of carbon is 6, so it should have 6 protons in total. So the number of protons is equal to the atomic number of an element. So the atomic number of sodium is 11, so it should have 11 protons, and we're supposed to distribute the 11 protons within the three shells here. All right, so the first one is has a maximum of 2, the second shell has maximum of 8, and so these add up to 10, and there's only one more proton remaining, so the other one electron goes into the M shell. So for carbon, the electronic configuration would be 2, 4, and for sodium, the electronic configuration would be 2, 8, 1. Alright, that's the first question. Second question, if the K and L shells of an atom are full, then what would be the total number of electrons in an atom? So the K shell can have a maximum of 2, and the L shell can have a maximum of 8. So when you add these up, the answer would be 10. Alright, that's how you do this. If they asked you if the K, L and M shells of an atom are full, then you would say the, let me clear this. Then you would say the maximum capacity of the K shell is 2, L shell is 8, and M shell is 18. So the sum would be 28, and that would be the answer. If the second question said if the K, L and M shells are completely full, the total number of electrons would be 28. But since they asked only if the K and L shells are full, the answer would be 10 here. And then we learned about valency in the previous chapter as well. But let's see what they have to say here. We have learned how the electrons in an atom are arranged in different shells or orbits. The electrons present in the outermost shell of an atom are known as its valence electrons. So if you talk about carbon and nitrogen and sodium, the electrons present in the outermost shell for carbon is 4. So the valency of carbon would be 4. And the outermost, the number of electrons present in the outermost shell of sodium is 1. So the valency of sodium would be 1. Okay, so we also know that the outermost shell of an atom can accommodate a maximum of 8 electrons. That's what we read in the previously in the lesson. It was observed that the atoms of elements completely filled with 8 electrons in the outermost shell show little chemical activity. And I want you to think about this question. Once I finish posing the question, pause the video, think about it, and play the video again once you get the answer. What type of atoms show little chemical activity? So what type of elements show little chemical activity? Think about it, pause the video here, and play it again once you get the right answer. Alright, so I hope everyone said inert elements or noble gases. That's another way of saying it. So this tells us that the atoms of elements with completely filled orbits who have 8 electrons in the outermost shell are inert elements. Okay, this is very important. I need you to remember this for the following concepts. Other words, their combining capacity or the valency is 0. So if you take neon has a valence, has the electronic configuration of 2, 8, and the number of electrons in its outermost shell is 8. But that doesn't make the valency of sodium of neon is 8. That makes the valency of neon as 0 because it does not have a lot of chemical activity. If you remember the actual definition of valency, you will remember that the valency is the combining capacity of an atom, and since atoms which have 8 electrons in their outermost shell do not combine with other elements, they have the combining capacity of 0. That is, they don't combine at all, which is why their valency is 0 instead of 8, even though they have 8 electrons in their outermost shell. So we have this table here, which is very important. I want you to know every element and its symbol, its atomic number, the number of protons, the number of neutrons, the number of electrons, the distribution, and the valency. Alright, I need you to know this. So if you see here, for helium, for neon, and for argon, in the first 18 elements, the valency is 0. And why is that so? Because if you see, the outermost electron has 8 electrons, outermost orbit has 8 electrons here and here. Okay, so I want you to know two things right now. There are two theories. So the first one is the duplet theory, D-U-P-L-E-T, and the second one is the octet theory. So the duplet theory says that if there are 2 electrons in the innermost shell or the K shell, then the combining capacity of that atom would be 0, right? So for helium, there is just 2 shells in the K shell, which is the outermost shell. So the combining capacity is 0, as you can see here, and that makes it an inert gas or an inert element. And if you remember from your chemistry, if you remember from other chemistry chapters, helium is an inert element, right? Helium is an inert element, and that is because it satisfies the duplet theory. Alright, an octet theory says that if there are 8 electrons in its outermost shell, whether it is the L shell, M shell, N shell, or any other succeeding shell, it would also have the valency of 0, which would make that an inert element as well. Alright, so this is known as the octet theory, and elements which satisfy either the duplet or the octet theory are inert elements. Alright, and then the number of protons is equal to the number of the atomic number of an element is equal to the number of protons, and that is equal to the number of electrons, and the number of neutrons is equal to the atomic number minus the mass number. Alright, so that's how you find all that. So for hydrogen, the mass number is 1U, for helium it is 4U, for lithium it is 7U, and according to that, oh I'm sorry, I meant M minus A. So mass number minus the atomic number will give you the number of neutrons. Alright, so these are two important formulae or relations, very important. Okay, so if you take the example of hydrogen, so the atomic number is 1 and the mass number is 1, so 1 minus 1 is 0, which is why there was a dash here in place of the number of neutrons. For helium, the atomic number is 2, the mass number is 4, so 4 minus 2 is 2. That's the number of neutrons. For lithium, the mass number is 7 and the atomic number is 3, 7 minus 3 is 4. Similarly, beryllium has 9U, boron has 11U, carbon has 12U, nitrogen has 14U, oxygen has 16U, fluorine has 19U, neon has 20U, and all this I remember because of a long time practicing it, because of years of practicing this. Alright, I don't expect you to know all this right now, but you should make a conscious effort and you should learn these, because that's going to help you in your board exams. It's going to help you a lot in your competitive exams like NTSE, NEET, and JEE. So I need you to remember the mass numbers, the atomic numbers, and if possible, the protons, electrons, and neutrons, the numbers, instead of sitting and calculating. This will save you an extra 5 seconds of time maybe that you can spend on another question, right? And then you will just distribute these into the KL and M and N shells based on the 3 rules that we learned previously in the lesson. Alright, so the combining capacity of atoms of elements, that is their tendency to react and form molecules with this atoms of the same or different elements, that is combining capacity, and that is the valency. Alright, so then an outermost shell which had 8 electrons was said to possess an octet, or you can say is said to satisfy the octet rule. Alright, and then we have atoms would react so as to achieve an octet in the outermost shell. So the main reason, so let's say, why do atoms react, right? So the answer to that question would be to attain stability. And how do they attain stability? By satisfying. Okay, so let me put that as another question. How do atoms attain stability? And the answer to this question would be by satisfying the duplet or octet rule. Alright, so these 2 questions are very important, and this is the reason behind so many chemical reactions. This is the reason behind all the combinations of elements and atoms that ever took place, because atoms react to attain stability, and they attain stability by satisfying the duplet or octet rule. Alright, so inert gases, like I told you before, they already satisfied the octet rule or the duplet rule in case of helium, so they don't react with another atom because they are already stable. So they have reached their purpose of existence, so to speak. So that's why they don't react with other elements. Alright, so the number of electrons gained, lost, or shared, this is another word that we will cover later. So as to make the octet of electrons in the outermost shell gives us directly the combining capacity of the element, that is the valency, discussed in the previous chapter. Alright, so for example, hydrogen, lithium, or sodium atoms contain 1 electron in their outermost shell, so therefore one of them can lose 1 electron. So it's easier for them to lose 1 electron is easier. This is easier than gaining 7 electrons, right? So imagine you have 1 chocolate, and your friend has 7 chocolates. Alright, so each time you so this is B and this is A, each time 1 chocolate is transferred, you lose a certain amount of energy. So if you give 1 chocolate, you lose a certain amount of energy. If B gives 1 chocolate, it loses a certain amount of energy. So in what way would the minimum amount of energy be lost, right? So if you give 1 chocolate, you would lose 1 unit of energy. But if B gives you 7 chocolates, it would lose 7 units of energy. So it would be easier for A to give 1 chocolate to B than B giving 7 chocolates, than the ease with which B would give A 7 chocolates. That's exactly how reactions between atoms is organized. It's easier to lose 1 electron rather than gaining 7 electrons, which is why hydrogen, lithium, and sodium lose 1 electron to satisfy their octet or duplet rules. Alright, so what is the valency of magnesium and aluminium? So Magnesium has 2, 8, 2 valency, and so it has 2 electrons here. It needs to reach 8 in its outermost electron. It doesn't matter whether it reaches 8 in the third shell or in the second shell. So would it be easier for magnesium to give 2 electrons or gain 6 electrons? Based on this example here about the chocolates, it would be easier for magnesium to gain 2 electrons. So its valency would be 2. Similarly, let me clear this part of it. For aluminium, the electronic configuration is 2, 8, 3. So the outermost shell has 3 electrons. So it has to attain the it has to satisfy the octet rule. So it has to have 8 in its outermost shell. Doesn't matter whether it's in the third shell or the second shell. So would it be easier for aluminium to lose 3 electrons or gain 5 electrons? Again, based on the example of the sharing of or the transfer of chocolates, it would be easier to lose 3 electrons, which is why aluminium would have a valency of 3. Alright, see, it's 2 and 3 respectively. Magnesium has 2 and aluminium has 3. Because magnesium has 2 electrons in its outermost shell and aluminium has 3 electrons in its outermost shell. If the number of electrons in its outermost shell is close to full capacity, then its valency is determined in a different way. So here's this trick that I remember. Let me, where do I want to take space here? Alright, let me clear this part. Alright, and here. So one way I remember the valencies is that I quickly write, I mentally remember the electronic configuration of an atom, of an element. That will happen with practice. So once you have that familiarity, this is an easy way to remember. If the outermost, let me take example of aluminium, and Y can be fluorine, let's say. Alright, so if the outermost shell of the atom has a number that is less than 4, so X is less than 4, then it would have less than or equal to 4, let's say. Alright, so the valency would be equal to the number of atoms in the outermost shell. And if the number of atoms in the outermost shell is greater than 4, but it's so if it's greater than 4, the valency would be equal to 8 minus X. So for in the case of Y, it would be 8 minus 7, which is 1, and the valency of fluorine is 1. Alright, and for X it would be just the number, so that would be 3, and that is the valency of aluminium. Alright, that's one way I remember it. I hope that helped you. I hope that helps you remember better in future once you have once you are familiar with the electronic configurations of atoms. Alright, so then we have a question: how will you find the valency of chlorine, sulfur and magnesium? So let's use my method here. Chlorine has an electronic configuration of 2, 8, 7. So this is greater than 4. So the valency would be 8 minus 7, which is 1. For sulfur is 2, 8, 6. So that is greater than 4. So 8 minus 6 is 2. For magnesium, Mg is 2, 8, 2, and that is less than 2 is less than 4, less than less than 4, not that. So that would be valency is equal to the number, so that would be 2. Alright, so then we have atomic number and mass number. Atomic number, we know that the protons are present in the nucleus of an atom. It is the number of protons in an atom which determines the atomic number, and it is denoted by Z. So previously when I was talking to you about the relation between atomic number, mass number, the number of protons, neutrons and electrons, I represented A as the atomic number, but it's actually Z because I didn't want to confuse you. I just used A as to represent it, but it's actually Z. Alright, so all elements of all atoms of an element have the same atomic number, and elements are defined by the number of protons they possess. Alright, so for hydrogen, Z is equals 1 because in hydrogen atom only one proton is present in the nucleus. Okay, and so the atomic number is defined as the total number of protons present in the nucleus of an atom. And then we have mass number. After studying the properties of the subatomic particles of an atom, we can conclude that the mass of an atom is practically due to protons and neutrons alone. So it's only because of protons and neutrons, electrons have no role to play in mass number. Okay, so since these are present in the nucleus of an atom, they are called nucleons, like I said before. Therefore, the mass of an atom resides in its nucleus because protons and neutrons are present in the nucleus. Protons and neutrons, that's P and N, and electrons are present all around the nucleus, right? That's minus. So since electrons have negligible mass, they don't account for most of the mass in no, I'm sorry, I intended to select the eraser. Since electrons have negligible mass, they don't account for most of the mass of an atom, right? So that's why protons and neutrons constitute most of the mass of an atom. That's why they said the mass of an atom resides in its nucleus. Alright, so then we have two questions again, but then before we move on to the questions, let's see how an atom is represented. So an atom is represented, let's say an element X has an atomic number A and a mass number, atomic number Z and a mass number A. Alright, this is how it is represented, with the mass number on top, atomic number below the, so the mass number is a superscript and the atomic number is a subscript, and the element is written normally. Alright, so for example, nitrogen is written as N7 as subscript, 14 as superscript, because this is the atomic number and this is the mass number. Alright, and we have two questions. If is that supposed to be number? I think so. So if the number of electrons in an atom is 8 and the number of protons is also 8, then what is the atomic number of the atom? So the atomic number is equal to the number of protons, which also happens to be the number of electrons, because the number of protons and electrons in an atom that hasn't undergone a reaction is the same. Okay, so remember that the number of protons is equal to the number of electrons in an atom which hasn't undergone any reaction. Okay, which hasn't undergone any reaction is an important clause. If it has undergone reaction, then they are not the same. So the answer would be 8. And what is the charge of the atom? So it would be 0, because the charge of an atom, if it didn't react yet, is neutral, which is why the charge would be 0. Find out the mass number of oxygen and sulfur atom. So oxygen, so the mass number is the sum of the protons and the neutrons, and in the table that they gave here in table 4.1, it should say that the mass number of oxygen is 16U and sulfur is 32U. Alright, this should be the answer. You can go back and check in the table. Alright, so isotopes. a number of atoms of some elements have been identified in nature which have the same atomic number, the same atomic number but different mass numbers. Alright, so there are a few atoms. When I was talking to you about the measurement of atomic masses in the previous chapter, I mentioned isotopes, and I said because of the presence of isotopes, oxygen, which was previously taken as the base element for measurement, was rejected, and carbon was taken because of its abundance as the C12 isotope. That's what we're talking about now. Isotopes are elements which have different mass numbers but the same atomic number. Alright, so hydrogen has H11, H12, H13. So this is protium, this is deuterium, and this is tritium. Alright, that's what the names are. For carbon it is C12 and C14. Alright, for chlorine it is 35 and 37. Alright, and then there's more for oxygen and many other elements, but these are the examples that they have given here. So on the basis of these examples, isotopes are defined as atoms of the same element. Atoms of the same element having the same atomic number but different mass numbers. Therefore, we can say that there are 3 isotopes of hydrogen atom, namely protium, deuterium, and tritium. Many elements consist of a mixture of isotopes. Each isotope of an element is a pure substance. The chemical properties of isotopes are similar, but their physical properties are different. This is important. Alright, the chemical properties are the same because of the same number of protons in each element, and because they have the same number of protons, they consequently have the same number of neutrons. When you're talking about an atom that hasn't undergone any chemical reaction yet, but their physical properties are different because of the different number of neutrons. Alright, yep. So how do we find the mass of a chlorine atom? We just average the masses of the isotopes based on the percentage of occurrence. So let's say the chlorine 35 isotope occurs 75% of the time. 75, that's 7. And the chlorine 37 isotope occurs only 25% of the time. So we would multiply 35 by 75% and add that to the 37, which is multiplied by 25%. Alright, and that would give 142 by 4, which is 35.5 U. Alright, and that's what they got here as well. So the mass of an atom of any natural element is taken as the average mass of all the naturally occurring atoms of that element. If an element has no isotopes, then the mass of its atom would be the same as the sum of the protons and neutrons in it. So if there is an element which has no isotopes, the mass number would be a straightforward sum of the protons and the neutrons without taking any averages. But if an element occurs in isotopic forms, then we have to know the percentage of each isotope form and then calculate the average mass. Alright, this does not mean that this does not mean that every atom of chlorine has a fractional mass of 35.5. It's just because we don't know whether we're taking the chlorine 35 isotope or the chlorine 37 isotope, that we take an average and assume that this is the average mass of a chlorine atom. Alright, so then moving back up, we have a few applications of isotopes. An isotope of uranium, that's a very famous isotope of uranium because it is used in nuclear reactors. An isotope of cobalt is used in the treatment of cancer. An isotope of iodine is used in the treatment of goiter. Okay, so this is a very famous and hopefully familiar isotope, the isotope of uranium. But these two, make sure you, if these two are not familiar to you, make sure you understand and remember which isotope is used for what. And then we move on to isobars, in which the number of protons is different, but the mass number is the same. So this is the complete opposite of isotopes, right? So isobars are completely antagonistic to isotopes, because isotopes have elements that have the same atomic number but different mass numbers, but isobars are elements which have different atomic numbers but the same mass number. Alright, I want you to remember the statement: isotopes are elements which have the same atomic number but different mass numbers, but isobars are elements that have different atomic number and the same mass number. Alright, and then we have two questions. For the symbol H, D and T, hydrogen, which is also called protium, deuterium and tritium, tabulate 3 subatomic particles found in each one of them. Okay, so you will find out how many the number of protons, the number of neutrons, and the number of electrons in each of protium, deuterium and tritium. Okay, and then write the electronic configuration of any one pair of isotopes and isobars. So I want you to go back to the lesson or rewind this video and see if you find examples of isobars and isotopes. Alright, so with that, we finished the lesson. Awesome, great job everyone. So these are just recap points that you can go through on the day of the exam or the day before the exam. And you have a few exercises that I would like you to try after you're sure that you have confidence in this chapter, and do so without going back to the tables given in the lesson, because then you will be sure that you have good understanding of the concept. All right, and then we have points to recap. Let me zoom out because that's too big. All right, so we learned about, in this lesson we learned about we started with the introduction of the structure of an atom. We talked about how there are protons, electrons and neutrons. We learned about the structure of an atom, and we did so using Thomsons Model of an atom, Rutherfords Model, and Bohr's Model of an atom. So Thomsons Model is also known as the plum pudding model. We also learned about that. And then we learned about the discovery of neutrons, mainly because of the absence of logic, and I explained the logic behind the discovery of neutrons. And then we learned about the distribution of electrons in orbits, the 3 rules. Let me mention here that we talked about the 3 rules. And then we learned about the valency. We learned about atomic number and mass number. Atomic number is represented by the letter Z, and mass number is represented by the letter A. And then we learned about isotopes, which have same atomic number, different mass number. And then isobars, which have the same mass number but different atomic number. Alright, so the difference between these two is very important. Very important. Alright, make sure you understood every concept very well. If you didn't understand any concept, or if you have a slight doubt, or if you have any doubt in any of the concepts, feel free to go back to the video where I explained that. Once you're trying the exercises, if you come across a question that isn't as easy as you thought it would be, refer to this video again, because I covered every concept in this chapter, and the exercises always cover every chapter from the every concept from the chapter. So if you don't understand anything, feel free to go back and watch the video again. Alright, so I hope this video helped you understand this concept better, and head on to the next video, which will start biology. This was the last chapter of chemistry. Yay us, we did this. So the next chapter is a biology chapter that talks about the fundamental unit of life, and spoiler alert, that is a cell. Alright, so I hope all of you understood this well, and don't forget that you can do this, and have a great rest of your day. Don't forget to like and share this video. Please subscribe to our channel for more content, and rock your exam. All the very best. Bye bye.